last lesson, you guys learned how to determine mass number, which is the number of protons plus the number of neutrons. But if you look at the periodic table, none of the masses, or very few of the masses that you will see on the periodic table, are whole numbers. Instead, they have decimals. And so the question is, why aren't they whole numbers? We said that mass number should be pretty much as close to a whole number as possible. You'll see that they're a tiny bit off of a whole number. However, they should pretty much be whole numbers because I'm adding protons and neutrons. But the thing is, the masses that you see on the periodic table, they are average atomic masses because most elements have at least two different isotopes. So for example, you guys saw hydrogen with a mass of 1, hydrogen with a mass number of 2, and with 3. The average atomic mass, what you see on the periodic table, is going to be an average of all of those masses. And specifically, it's going to be a weighted average, okay? Because certain isotopes are more common than other isotopes. So let's use this concept to learn how to calculate the atomic mass. And we're going to just jump in using an example. So here I've got two naturally occurring isotopes of copper, copper-63 and copper-65. Now, copper-63, the actual mass of copper-63 is 62.93, while the actual mass of copper-65 is 64.93. But these values are rounded, so that's why it's 63 and 65 instead of those. All right, so what we're going to do to find the average atomic mass, notice that copper-63, its abundance is 69.2%, while the abundance of copper-65 is 30.8. So I can't just add these two numbers together and divide by 2, because if I did that, what I would be saying is that each of them have the same abundance, and they don't. So instead, I'm going to do a weighted average. To perform a weighted average, what you do is you're going to take the first mass, so 62.93, because that is the mass of copper-63, and you're going to multiply it by its abundance, its percent abundance. But we got to make that into a decimal. So I'm going to move my decimal place 2 places to the left to get 0.692. Okay? Then I'm going to add to that the mass of copper-65, which is 64.93, and I've got to multiply it by its percent abundance, which would be 0.308. Okay? And then I can add those two together, and I get 63.546. Now, really quickly, I know the question is going to be rounding. For rounding, I'm going to, for all of these problems, I'm going to round to the hundredths place. So that 4 is going to round to a 5, so it's going to be 63.55, and the units for average atomic mass are AMU. Now let's make sure that this answer makes sense. All right, the relative abundance of copper-63 is 69.2%, while if 65 is only 30.8%. So it makes sense, since copper-63 is more abundant than copper-65, that the average atomic mass of copper should be closer to copper-63. And it is, because the average atomic mass is 63.55. All right? So how to complete these problems, how to calculate average atomic mass. You take the mass number, or the mass of each isotope, multiply it by its percent abundance, but made into a decimal. Then you add those values together, and there is your average atomic mass. And that's it.